Alright fellas, so today's problem is going to be merge two sorted lists. We are given heads of two sorted lists, list 1 and list 2. And we have to merge the two lists into one sorted linked list and return the head of the new sorted linked list. So this is list 1, this is list 2, and our job is to create this sorted list like so. And then this last clause here, the new list should be made up of nodes from list 1 and list 2. So what does that mean? You don't really have to be a genius to kind of figure out what the algorithm is, right? Generally speaking, you probably have some kind of pointer in here and pointer in here, and then whichever one is smaller we take, and that's going to be our first element. And then we increment this here, and then since this is smaller than this, then the next element would be a 1, increment this here, this is smaller than this, and so on and so forth, right? Now the thing with this clause here is that we don't want to be creating new nodes every single time, because all of these are objects, right? And the cleaner but more expensive way to do this is we create a copy of this object, which is this guy, which points to this thing, which we're also going to create a copy of, and same thing with this one. So they don't want us to be creating copies when we do this. What they do want is when we say 1 points to 1, they want us to sever this link and then point an arrow to this node. And well, this arrow is fine. We don't have to do anything about it. And when we want to point 2 to 3 for this here, we sever this link and point it to 3 and so on and so forth. By doing it this way, the new list will be made up of nodes from list 1 and list 2. We're reusing the nodes here, right? So how do we solve this? Okay, so let's get started. We probably want some kind of while loop, right? And we want this while loop to keep going as long as either tail1 or tail2 is not none. We're going to handle the null cases soon, don't worry. So to start, if tail1.value is smaller or equal to tail2.value, then we want to append this to our answer, right? And in the else case, we want to append tail2 instead. So then we need some kind of result, right? Some kind of result variable to hold it in, right? But remember, we're working with the linked list here. So we need one variable to keep track of the head because we're going to be returning the head. And then we need another variable called tail. And this is going to be where we're going to be appending stuff to. So right now, they're both none, right? They're not pointing to anything. So we want to do like result tail dot next is equal to tail1, right? Now you can already kind of see the problem if we initialize this thing to none, because let's say our result tail and our result head is already initialized properly at 1, 1, then this code would work, right? Well, in this case, tails2 is going to win. So we take this node, the next value of this is going to be 1 from list 2. And then we can move, oh, sorry, this is supposed to be tail1. And then we move tail2 here, and then we check again. This one's going to be appended next. So this is going to run result tail next. Result tail is this. The next node is going to be 2. That's what we want to happen. But unfortunately, because these two are initialized to none, we can't do none.next. That's going to cause an error. So the easiest solution, without writing a separate block in the beginning to initialize these values, which is going to make our code super long because the code to initialize is basically the same code as the loop, right? So the easiest way to do this is to create a dummy node. So if I create a node, just an empty node like this, and when you create an empty node and you don't pass in any parameters, let me just show you here. The default value is going to be 0, and then it's going to be pointing to none, right? So we're going to use this, which essentially just creates a dummy node, and then we're going to append the elements to it, right? And then at the end, all we have to do is return the result.head, which is this thing, dot next, which is this guy, and this is going to be our answer. So let's do the dummy node strategy. It's going to save us a lot of code. But of course, with our result tail, we don't want to be creating a new instance of a dummy node. We want the result tail to be pointing to the same node as the result head, which is why we're going to initialize result tail to result head. Wait, now they're pointing to the same node here. Let's continue with our code. We got a bit sidetracked, but let's start again. So let's run the loop again. Is either tail1 or tail2 a valid node? Well, looks like neither of them are none, so we can continue with the loop. First one, this guy executes. We're going to take tail1. We're going to point this guy to tail1, and then we want to move tail1 to tail1.next, right? We've already used this element. We've already appended it to our result. So we can move tail1 to the next element. Here, we want the other to do the same. And lastly, we want to increment our result tail in both cases. So when we append the new element, we append it to our latest node. Res tail equals to res tail.next. So let's run the loop again. This time the value at tail2 is smaller than tail1, so the else block is going to execute. Let's see what happens in the else block. Result.tail, which is this guy, dot next, this arrow is going to be going to tail2. Okay, so we redirect this like that. And then tail2 is going to be moved to tail2.next. So whatever this thing is pointing to, tail2. And the result tail is going to be moved to the result tail.next. So this here, res tail. And we just kind of repeat this. It's not the most complicated algorithm, right? So let's just get through it. So the last iteration here, we change res.tail to this number 4, move tail1 to none now, because this is pointing to none, right? 5 is also pointing to none, and then we move res tail. Now, since tail1 is pointing to none here, then we want this else block to execute, right? So this, we only want this to execute. I need a bit of space. So tail1 and, so this just means that it's not null, and the condition that we had before, .val less than equal tail2.val. We only want it to execute if tail1 has something, or the other condition is if tail2 is none. Well, in this case, it's flipped, right? So in this case, tail1 is the one that's none. So this thing fails. And this thing fails, so this else block is going to execute, and we're going to append this to our result, res tail. And now both of them are none, so this while loop's going to break, and all we have to do is return res head.next, which is this guy. And that's about it. Let's copy paste this to the editor. All right, so I just copy pasted the code. Let's just run it. Yeah, there you go. This thing works. One note is that it's actually possible to simplify this a little bit further. So instead of running an or, we do an and. This while loop is only going to execute if both tail1 and tail2 have something, right? So imagine you were like merging your list or whatever, and then in the end of it, you find out that tail1 is none, and then tail2 has like a bunch of items, right? 5, 6, 7, 8, 9, 10, whatever, right? If we were to do it our way here, then we would execute this else clause over and over again, appending 5, append 6, append 7, append 8, append 9. But we don't need to do that because once tail1 is none, we just take the remainder of what's left in tail2, and then we just append that into our result. And that's kind of the idea of the small optimization. So because we're only running it if both of them have values, then we don't have to do any of this none checks anymore. All we have to do is check their values. And then in the end, if we have access in like, let's say tail2, then we just append tail2 to our result. Result.tail.next is equal to tail1 or tail2. So if tail1 is empty and tail2 is not, then we append tail2 to next. If tail2 is empty and tail1 is not, then we append that to our result tail. And lastly, if neither of them are true, then next is going to be pointing to none, which it already is. So this is the optimized answer. So now the coding's done, let's talk about time complexity. So we're processing literally every single node one time. And because of that, the time complexity is very clearly O of m plus n, where m is the size of this one and n is the size of this two. As for the space complexity, we are not using any extra space. We are reusing all of the nodes that's given to us from list 1 and list 2. We're not copying and we're not making new nodes or anything like that. So the space complexity is O of 1. And that's about it. Thanks for watching. Okay, bye.